Hello, my name is Sandhya Pawar and I am MSc Part 2 student from Department of Physics, Mumbai University. My presentation topic is electrical properties of the ceramic. So, let's start with my presentation. The first question arises is that why we use the ceramic. As we all know, we use various metals and non-metals for various applications, but some of them have certain limitations when we use them in a high temperature region or in a chemical environment. To overcome this limitation, a new class of material are introduced and we call them as a ceramic. So, what is ceramic? Ceramic are the inorganic and non-metallic material. Most of the ceramic are the compound between metallic and non-metallic elements for which interatomic bonds are either totally ionic or predominantly ionic but have some covalent character. The term ceramic comes from Greek word keramikos, which means that burnt stuff, indicating that the desirable properties of this material are normally achieved through high temperature heat treatment process. Until the past 16 years, the most important material in this class were termed as a traditional ceramic, for which the basic components are clay, silica, feldspar. An example of traditional ceramics are bricks, tiles and electrical porcelain. The significant process has been made in understanding the fundamental characteristic of this material and the phenomenon that occur in them that is responsible for their unique properties. A new generation of this material has been evolved and we call them as the engineering ceramic. The engineering ceramic consists of pure compounds such as aluminum oxide, silicon carbide and silicon nitride. They have dramatic effect on our life and we use them in electronic, computer, communication and aerospace applications. The next point is properties of ceramic. The properties of ceramic vary greatly due to difference in their bonding. In general, ceramic are hard and brittle with low toughness and ductility. They are good electrical and thermal insulator due to absence of conduction electron. Normally, they have high melting temperature and high chemical stability. Some of the ceramic find application in the capacitors. They are chemically stable and has good wear resistance. They are prone to thermal shock and oxidation resistance is very high, means they are not easily oxidized. Because of these properties, ceramics are indispensable for many engineering designs. The next point is basic properties of dielectric or insulant. Let's first see what is dielectric material. Dielectric material is the one that is electrically insulating and exhibit or may be made to exhibit an electrical dipole structure. That is, there is a separation of positive and negatively charged entities on molecular or at atomic level. The first properties of this dielectric material is dielectric constant. Suppose if we have a capacitor and we apply voltage across it, then one plate of the capacitor is positively charged and other is negatively charged. Then capacitance C is given as the quantity of a charge stored on either plate Q by the voltage V that is applied across the capacitor, and the unit of capacitance is farad. Now if we consider a parallel plate capacitor with vacuum in a region between the plate, then capacitance is given as C is equal to epsilon naught A upon D, where A is the area of the plate, D is the distance between the plate and epsilon naught is permittivity of a free space. If we inserted dielectric material in a region between the plate, then capacitance is given by C is equal to K epsilon naught A upon D, where K is the dielectric constant which increases the charge storing capacity of the capacitor. The second properties of this dielectric material is dielectric breakdown strength, which measure ability of a material to hold the energy at high voltage and define as a voltage per unit length at which failure occurs. The maximum electric field that dielectric can maintain without electrical breakdown. The dielectric breakdown strength measured in volt per milli. If we dielectric is subjected to voltage gradient that is too intense, the strain of electron and ion increases, which increases the strength, and dielectric material begins to break down and current passes between the plates. The third property of this dielectric material is dielectric loss factor. If we inserted real dielectric in capacitor, then current lead by the voltage by 90 degree minus delta, where delta is the dielectric loss angle and the product K tan delta is a loss factor which measures energy lost by the capacitor in AC circuit. The next point is ceramic insulator. Ceramic material have electrical and mechanical properties which make them suitable for many insulator applications in electric and electronic industry. The ionic and covalent bonding in ceramic restricts the electron and ionic mobility and thus make them good electrical insulator. This bonding makes most of the ceramic strong but relatively brittle. The structure and properties of several insulator ceramic materials are discussed as follows. The first material is electrical porcelain, which consists of 50% clay, 25% silica and 25% feldspar. This material has good green body plasticity and wide firing temperature range at low cost, but the major disadvantage of electrical porcelain is it has higher power loss factor. The next material is statite. Statite consists of 90% talc and 10% clay. They are good electrical insulator because it has low power loss factor, low moisture absorption and good impact strength. The third material is forsterite, whose chemical formula is Mg2SiO4. It has no alkali ion in vitreous phase, so has higher resistivity and lower electrical losses with increasing temperature. Also, it has lower loss of dielectrical property at higher frequency. The next material is alumina. The alumina ceramic have relatively high dielectric strength and low dielectric losses along with high strength. The sintered alumina widely used as a substrate for electronic device application because it has low dielectric losses and smooth surface. Now let's discuss some ceramic material that are used for capacitor. Ceramic material are commonly used as a dielectric material for the capacitors. Example is this ceramic capacitor. This flat disc ceramic capacitor consists of barium titanate along with other additives. Barium titanate has very high dielectric constant of about 1200 to 1500. The additive increases the dielectric constant of barium titanate. The ceramic chip capacitor used in thick film hybrid electronic circuit as they have high capacitance. The next point is ceramic semiconductor. Nowadays, semiconductors are widely used in various applications because it has lower band gap than metal and insulator, also has various properties which make them suitable for various electronic applications. Now we will discuss various ceramic compounds that have semiconducting property and that are important for operation of some electrical device. Example of such electrical device is thermistor, also called as thermally sensitive resistor, which used for temperature measurement and the control. The negative temperature coefficient, that is NTC type thermistor, whose resistance decreases with increasing temperature, means as we increase the temperature, thermistor becomes more conductive. The ceramic semiconducting material used for negative temperature coefficient thermistor are the sintered oxide of manganese, nickel, iron, cobalt and copper. The solid solution of combination of oxide of these elements used to obtain necessary range of electrical conductivity with temperature change. The example of ceramic compound is magnetite, whose chemical formula is Fe3O4, which has low resistivity of about 10 to the power minus 5 ohm meter compared to 10 to the power 8 ohm meter for most regular transition metal oxide. It has inverse spinel structure and good conductivity due to random position of Fe2 plus ion and Fe3 plus ion in the inverse structure. The electrical conductivity of metal oxide compound for thermistor can be controlled by forming solid solution of different metal oxides. The next point is ferroelectric ceramic. Let's first see what is ferroelectric material. The ferroelectric material exhibits spontaneous polarization. that is polarization in absence of electric field. Some ceramic ionic crystalline materials have unit cells that do not have center of symmetry, so their unit cell contains small electrical dipole. Example is barium titanate. Above 120 degrees Celsius, the barium titanate has a regular cubical symmetrical structure, and below 120 degrees Celsius, the central titanium 4 plus ion and surrounding O2 minus ion, as shown in figure A of barium titanate unit cell, shift slightly in opposite direction and create the electrical dipole moment. The shifting takes place at a critical temperature known as Curie temperature, and crystal structure of ceramic changes from cubic to tetragon. On large scale, barium titanate has a domain structure in which small electrical dipole of a unit cell line up in one direction. If we consider a polycrystalline barium titanate is slowly pulled through its Curie temperature in presence of strong electrical field, then dipole of all domain line up in a direction of electric field and produces a strong dipole moment. The last point is piezoelectric ceramic. Let's first see what is piezoelectric effect. Piezoelectric effect is an electromechanical effect by which mechanical forces on ferroelectric material produces electrical response or electrical forces produces mechanical response. Barium titanate and other ceramic exhibit the piezoelectric effect, which schematically illustrate in figure below. Let's consider a ferroelectric ceramic that has resultant dipole moment as shown in figure A. In this material, there will be an excess of positive charge on one end and excess of negative charge at other end in the direction of polarization. Now, a compressive stress are applied to the material as shown in figure B. The stress reduces the length of a sample between applied stress and reduces the distance between unit dipole. So, reduce overall dipole moment per unit volume of the material. The change in dipole moment changes the charge density at the end of a sample, so it changes the voltage difference between end of the sample if they are electrically insulated from each other. Now, if we apply electrical field across the sample as shown in figure C, the sample is slightly elongated due to increased positive charge that attracts the negative pole of a dipole and reverse at other end of the sample. The piezoelectric ceramic have many industrial applications as follows. The first one is the compression accelerometer, which measures the vibratory acceleration occurring over wide range of frequency. Second one is ultrasonic cleaning transducer, which converts electrical forces into mechanical response. And the last one is PZT ceramic, which made from solid solution of lead zirconate and lead titanate. They have broader range of piezoelectric properties such as higher Curie temperature than barium titanate, so they are superior than barium titanate. Thank you.